All right, so triacylglycerols we've talked about. So the triacylglycerol has a glycerol portion, which is a 3-carbon alcohol. And each of those oxygens is tied up in an ester with a long-chain fatty acid, which I'm just going to draw as R here. This portion, again in pink, is the fatty acid, which is just a long-chain carboxylic acid. And then this portion in orange is going to be the glycerol portion. Sorry, I'm getting a little bit mixed up. So these are the fatty acids, and this is the glycerol portion. And we'll talk when we get to metabolism about how nature hydrolyzes this ester linkage between glycerol and the fatty acid. The enzyme that does that is called a lipase. We'll talk about the amino acids in the active site that make that happen. When that happens, the molecule gets broken up into, so if we write hydrolysis here, you get 3 of the fatty acids, the 3 of the carboxylates, and 1 glycerol, which is just this 3-carbon alcohol. All right, and then nature will take the fatty acid, metabolize it into acetyl-CoA, individual chunks of acetyl-CoA, and then nature will take glycerol and modify it a little bit and take it to the metabolic pathway called glycolysis. So this is one reason why triglycerides are among the class of hydrolyzable lipids, because nature can break them down. Okay, let's talk briefly about fatty acid properties and how they're related to the properties of the various kinds of triglycerides. So this is something you probably learned maybe in 351 when we talked about non-covalent interactions. I'm going to list here a couple of different saturated fatty acids. They're called saturated because they lack double bonds. And then over here we're going to list some unsaturated fatty acids. They're called unsaturated because some of the carbons are not fully saturated with hydrogen. They have some double bonds. So here we're going to write number of carbons, and then I'm going to show you melting point. And this is going to be just a quick review. These numbers aren't for you to memorize, but you should be able to rationalize the increases in melting temperature or melting point with fatty acid structure. For example, if we elongate a fatty acid from 12 to 16 and then to 18 carbons, you'll see that the melting point increases from 43 to 63 to almost 70, and then at 20 carbons it's up at 77. So what's the rationale for that? Why does melting temperature increase as the length of the hydrocarbon chain increases? What's the explanation for that? I'm hearing London dispersion forces, I'm hearing van der Waals interactions, right. So as the surface area, as nonpolar surface area increases, then the strength of what we're going to call van der Waals interactions increases as well. And van der Waals interactions is the same thing as London dispersion forces, is the same as induced dipole interactions. Any questions about what an induced dipole interaction is? Okay, good. So let's now look at unsaturated fatty acids of approximately the same molecular weight and see if we can rationalize this. So we'll start number of carbons and then melting point. Again, these aren't numbers to memorize, but you should be able to rationalize the trends. I'm going to put double bonds here, dB for double bonds, and we're just going to write the position and the stereochemistry of the double bond. So if we have a 16 carbon chain with a single double bond at carbon 9 that's in the Z configuration or cis, the melting point is 0. Now that's you should sort of gasp a little at that. It used to be, there you go, good. It used to be 63, now it's 0. All we did is put in 1 double bond. So that's a pretty dramatic change. Similarly, there are various 18 carbon fatty acids. One that has just 1 double bond and its melting temperature is 13. But there are other 18 carbon fatty acids that have 2 double bonds. This one's melting point is minus 12. And then there's one that has 3 double bonds at 9, 12, and 15. And that melts at minus 16 C. So the 18 carbon fatty acids with 3 double bonds is a liquid even below 0. It's a liquid when water is solid, even though it's enormous, right? And so we need to sort of talk about why that is. And then I want to just, before we do that, I want to illustrate, I need just a little bit more space, let's see. The 20 carbon, I'll pull this one down a little bit for comparison. The 20 carbon fatty acid that's called arachidonic acid actually has 4 double bonds at positions 5, 8, 11, and 15. Those are all Z, and its melting temperature is minus 50. So you can see the trend, right? 1 double bond drops the melting point down by 60 degrees roughly. 2 double bonds, 3 double bonds by even more. By the time you get 4 double bonds, look at that differential. It's 120, almost 130 degree difference in melting temperature. So let's talk about why that is, and we're going to illustrate that with the structure of some of these fatty acids. I want to actually name some of these. I'm not going to require you to know the names, but you're going to hear the names a little bit here and there. The one double bond 18 carbon fatty acid is called oleic acid. The 2 double bond 18 carbon fatty acid is called linoleic, and the 3 double bond fatty acid is called linolenic. This 20 carbon fatty acid with 4 double bonds is called arachidonic acid. And this one's important because it's a precursor for the prostaglandins. I'm just going to draw for you real briefly the linolenic fatty acid, and we'll talk about its structure. So here's the carboxylate. Here's the carbonyl carbon, the alpha carbon. We're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. And at carbon 9, we're going to have a double bond between carbons 9 and 10, and its configuration is going to be Z. So that's 9, 10, 11. Then we'll go to carbon 12, and at carbon 12, we're going to have another double bond, and its configuration is going to be Z. 13, 14, 15. At carbon 15, we've got another double bond whose configuration is Z. 16, 17, 18. So this is carbon 1, this is carbon 18. This is linolenic acid. So what's the rationale for why linolenic acid has such a lower melting point than the fully saturated 18 carbon carboxylic acid? What do the double bonds do? Somebody raise your hand. Yeah, go ahead. Inhibit stacking of what? Right, so the dispersion forces are stronger when the fatty acid chains can get close together, right? Contact surface area maximizes induced dipole interactions. The double bonds inhibit close packing or stacking of the hydrocarbon chains. And this then decreases the strength of the van der Waals interactions that hold individual molecules close to each other. Weaker van der Waals interactions mean lower melting point. You don't have to apply as much energy to get the fatty acid molecules to move further away from each other. Okay, that's important. You guys, does that make sense? I think you've heard about that before, but that's an important thing. Yeah, go ahead.
What if all the double bonds were in the E configuration?
Right. What if all the double bonds are in the E configuration? So in the E configuration, they can get close to each other again because they can stack side by side in the sort of zigzag shape. So if they were trans, if the double bonds were trans, you would see the melting points increase again. So that allows us to talk real briefly about a couple of things related to stuff you hear, food science, epidemiology, and so on. Do you want to say? Sure. Hold that thought on the trans fatty acids in just a little bit. We'll come back to that because we're going to talk more about the kinds of lipids that are in different triglyceride sources. One important thing to note about linolenic acid, it is an example of what we call an omega-3, that's the Greek letter omega, sorry, it looked kind of funny, omega-3 fatty acid. So why is it called omega-3? Well, you guys know that when we're talking about carbons and counting carbons, we frequently use Greek letters to describe the relationship between various atoms. For example, this is the alpha carbon, it's adjacent to the carboxylic acid. This is the beta carbon, it's adjacent to the alpha carbon. We don't have enough atoms to run all the way through the Greek alphabet here, but one convenient way of talking about the end of a carbon chain is to call the one at the end the omega carbon. Okay, so alpha to omega, right? Beginning to end, first and last. We got some scriptural things going on there. So an omega-3 fatty acid is a molecule that has a double bond, 3 carbons from the end. So this is the omega carbon. You count 1, 2, 3, and then there's a double bond there. That's why it's called an omega-3 fatty acid. These are thought to have some health and nutritional benefits, thought to be protective against various things. I don't understand the food science or the epidemiology. Some of you may have read about that. But I do know that there are products advertised to you as being rich in omega-3 fatty acids, particularly eggs. All they're doing is they're incorporating a lot of omega-3 fatty acids in the chicken feed. And then the chickens produce eggs that are rich in omega-3 fatty acids. In general, unsaturated fatty acids have better health effects than the fully saturated ones. But let's talk briefly about the kinds of fatty acids that are present in triacylglycerol. So understand what we've done. We started with the triacylglycerol. We zoomed in on the component of the fatty acid. I'm showing you melting points of fatty acids, not melting points of the corresponding triglycerides. But in general, the melting points of the triglycerides will track with the melting points of the fatty acids. So you would expect a triglyceride composed of mostly saturated fatty acids to be a solid at room temperature. You would expect a triglyceride composed of mostly unsaturated fatty acids to be a liquid at room temperature. So here are some sources of fats and oils that you may be familiar with. Animal fat, so this is sometimes called tallow, or my favorite, lard, or in Spanish, manteca. There's a really great jazz song called Manteca Sunrise. If I served my mission in the Rio Grande Valley in Texas, and we always went to buy our groceries at La HEB, which is what we called it. You don't have to speak Spanish in Texas to go to grocery shopping. So my gospel Spanish is decent. My La HEB Spanish is not very good at all. But anyway, I remember that you go to HEB and you could buy 5-gallon buckets of manteca in big yellow, kind of like the big Home Depot buckets, except they're yellow with the red lid, and it said manteca on it, and it was 5 gallons worth of lard. Now, what do you need that much lard for? Tamales. It's so good. So anyway, fun memories. I've had some good tamales, but since then, but nothing like in the Rio Grande Valley. So fatty acid composition of various fats and oils. We're going to sort of give you percentage-wise of saturated, and again, we're just zooming in on the fatty acid component of the triglyceride. Over here, we're going to write the unsaturated fatty acid component, mostly focusing on the 18 carbon monounsaturated and the 18 carbon diunsaturated fatty acids, 9Z and 12Z. And I'm just going to give you a percentage of unsaturated versus saturated fatty acids in each of these sources. So, for example, animal lard, or fat, or manteca, is mostly saturated fatty acids. Percentage-wise, it's about 25% 16 carbon, 15% 18 carbon, about 50% unsaturated, and about 6% diunsaturated. So I guess I said mostly saturated. It's actually mostly unsaturated, but with a substantial component of saturated fatty acids. And if you've ever dealt with animal fat before, is it a liquid or a solid? Solid, right? So apparently having that much unsaturated, sorry, I'm confused. No, I was looking at my notes and I was confused by something I wrote. Apparently having that much saturated fatty acid is enough for it to be solid. Let's look at olive oil. So it's now much smaller composition of saturated fatty acids, about 80% oleic acid, the monounsaturated, and about 7% the diunsaturated. These numbers don't add up to 100 because there's components here that I haven't written down, and that's fine. Peanut oil, here's a fun story. So peanut oil is mostly, again, unsaturated, about 60%, monounsaturated, about 20% diunsaturated. So it should be both olive oil and peanut oil are liquids. Okay, so if peanut oil is a liquid, then how come when you go buy a jar of Skippy, it's a solid? What have they done to it? Well, they can add an emulsifier. Sure, emulsifiers can cause the fat to mix in with other stuff and not separate, but they've also done something else, which is what? Hydrogenation, right. What happens when you take 18 carbon fatty acid like linoleic acid and then you run it over palladium on carbon with hydrogen? What do you get? You get the 18 carbon fatty acid that is saturated, right? I'm not going to draw it, but all the double bonds get reduced to alkanes. What would that do to the physical properties of the fatty acid? Reduction from the alkene to the alkane. Melting temperature increases. Now it's a solid, right? So this process of reducing the double bonds in triglycerides and fatty acids is called hydrogenation. So if you take your jar of Skippy and you look on the back, it's going to say hydrogenated soybean oil, meaning they took oil, vegetable oil from soybeans or some other source, and they hydrogenated. Why did they do that? They wanted it to not be a liquid, they wanted it to be more of a solid so that it wouldn't separate out. Now, when you go to buy, if you're feeling particularly posh and you've been influenced, perhaps you want to buy the super organic, unmodified peanut butter, Adam's peanut butter or whatever it is. You go to the store, you buy it, and up at the top is what? A layer of oil. And it's there, why? Because they didn't hydrogenate the double bonds. It's still a liquid. Now you can slurp the oil off the top if you want. Extra credit. Good. You'll do it. Take one for the team. You got to stir it up, and you got to do so regularly to incorporate the oil in it. Now, there's another reason why people hydrogenate unsaturated fatty acids, and here is an important reason. The double bonds are, so another reason for why hydrogenation is that the double bonds are reactive as nucleophiles. You know this because you took 351, where double bonds could add to electrophiles. The most insidious electrophile for double bonds in our atmosphere is oxygen. Double bonds are subject to oxidation in an atmosphere of oxygen. So let me show you an example of what can happen. We're going to zoom in on just this carbon of linolenic acid, and I'll show you briefly a reaction that can occur. So oxygen, if you didn't know this, if you look at its MO picture, even though we draw its Lewis structure like this, that's sort of inaccurate. Oxygen is mostly a diradical. You can draw it like this, and that reflects more likely what its state is in our atmosphere. And so it can abstract a hydrogen from this doubly allylic carbon 10 or carbon 11. Why is that CH bond weaker than the other CH bonds in the molecule? Ideas? Somebody raise your hand? No? Nobody willing to commit? You got this. Come on. Go ahead.
Because surrounded by two double bonds, two carbons that are sp2 hybridized.
Surrounded by two double bonds, two carbons that are sp2 hybridized, which means that if we do homolytic bond breaking of that CH bond with a radical, which oxygen is, oxygen abstracts a hydrogen atom from that carbon, giving you, after the reaction on this side, you've got, a peroxy radical. And on the other side, with what's left over here, is a resonance stabilized radical. So the moral of the story is that allylic carbons, carbon 11 is a doubly allylic carbon, meaning it is adjacent to two double bonds, results in a resonance stabilized radical. And so oxygen can easily remove a proton there. What ends up happening is that that peroxy radical can recombine with the allylic radical to give you a fatty acid which now has a new unnatural, or a new, shouldn't be there in the first place, carbon-oxygen bond. Okay? And that can, the peroxy radical can be reduced, it can turn into an alcohol or other things. But oxidation of fatty acids results in what we call rancidity of oils and fats. Okay? So, some of you probably during your missions carried around a little vial of consecrated oil, unsaturated olive oil, in very, very hot climates. And you did that for several years, and then perhaps afterwards opened it up and it smelled terrible, right? If you've done this? What happened is the double bonds oxidized. Now, I don't know that there's any official doctrine about the extent of oxidation before the oil becomes unconsecrated, but you should replace that, okay? And this allows me to tell you a story of why my mother doesn't believe that I am an adult yet. I'm 45 years old. So every couple of weeks we go to my mom and dad's house in Lehigh for what she calls Grammy Sunday. And it's a highlight. The grandkids love to come, and we eat Sunday dinner together and talk, and the grandkids play. They sneak off to the basement to play the Wii. Yes, my parents still have a Wii, and so, which they never have used, which is why it's still functioning. Ours is busted, but we were going to have tostadas one Sunday, and my one job was to bring the tostada shells and the shredded lettuce. So I'm really good at shredding lettuce, I can do that. I reached into the pantry and I pulled out the tostada shells, they looked good. We went to the meal, we started eating, and start biting into that tostada shell, which has a lot of oil in it, and it tasted kind of funny. If you ever tasted rancid oil or smelled rancid oil, there's something kind of off. And it turns out that the tostada shells I had used were kind of old because we don't use them that frequently at our house. So we had them, they were there, like, oh, these will be fine. No, the oil had gone rancid. So I often tell my mom, I'm an adult, I can do more, but the one time I had a job, which was to bring the tostada shells, I brought rancid tostada shells to Sundays. So trying to do better, trying to earn back confidence. Okay. Let me show you one plant-derived oil that is mostly saturated. So, coconut oil. You can buy this at the store. They call it coconut oil. I think they call it oil because it's isolated from plants, but it is 86% a composition of 14, 16, and 18 carbon fatty acids. I don't know what the breakdown is, so I just put 86% overall saturated fatty acids, only 7% unsaturated. And so you'll notice you buy coconut oil and it's a solid. You heat it up a little bit, it can become a liquid again. One of my sons likes to put it in his hair, but if it's cold outside, then his hair gets really crinkly, which is because why? The coconut oil freezes. So you got to be careful. Okay. So just backing up to rancidity, one reason why people hydrogenate oils is for shelf stability. If you take a product that's made with hydrogenated vegetable oil, there aren't any double bonds in there, so your crackers, your cookies, your tostadas, your chips can be on the shelf for a long time. They're not going to oxidize and go rancid. However, if you use unsaturated fatty oils, then you're going to have some shelf stability issues. They're going to expire earlier. The taste is not going to be good earlier. Now, why would you ever then use unsaturated fatty acids? Well, first, they're healthier. And then second, the process of hydrogenation is sometimes incomplete. It's reversible, and sometimes when you hydrogenate an oil, you actually get double bond isomerization. And this is where a double bond in the fat or oil can go from cis to trans. And that's where the term trans fats come from. Fats or oils that have been partially hydrogenated likely have some composition of trans fats. I, again, don't know the food science or the epidemiology on this, but trans fats are associated with some negative cardiovascular outcomes. Again, this mostly affects your life in terms of the way food companies advertise to you. They will say this is trans fat free, meaning it has not that term actually doesn't mean it has 0 grams of trans fat. It means it has less than maybe 500 milligrams of trans fat. So 500 milligrams equals 0 or something like that. Anyway, but the reason trans fats are present is because they partially hydrogenated some oil, because nature doesn't make trans fats in general. The trans double bonds are not found in unsaturated double bonds from nature, right? Unsaturated fatty acids and triglycerides from nature. Okay, any questions you want to ask about that? Okay, happy cooking and good luck with slurping that peanut oil off the top. Don't do that, that's gross. All right, now let's see. So we have done waxes. We have done triglycerides. Let's talk briefly about phospholipids. This is something that I think that you've gotten before, and so we won't spend a tremendous amount of time on it. Phospholipid is derived from a triglyceride. The phospholipid also is also based on an ester with glycerol, but in the phospholipid, one of the 3 OHs from glycerol is tied up with a phosphate group, and then over here there's something else. So again, in pink is a long chain fatty acid. I'm going to leave that to your imagination. This is going to be, 14 to 18 carbons long. It could be saturated or it could be unsaturated. In orange is the glycerol portion. And then in blue, I'm highlighting in blue because it's sort of water soluble, you have this polar head group, okay? And depending on the phospholipid, the R is going to be different. So here are some things R can be. R, here the squiggly line indicates the connection to the phosphate. It can just be a negatively charged oxygen. So that's called phosphatidic acid when you have just the phosphate group here. If that oxygen is no longer negatively charged, but it's bonded to two carbons with a positively charged nitrogen, ammonium ion on it, this group is called ethanolamine. So we would call that group phosphatidyl ethanolamine. And that will be, people that talk about lipids a lot abbreviate these, so PE is phosphatidyl ethanolamine. If you take the same sort of ethanolamine structure, but you modify the nitrogen with methyl groups, it's positively charged. That two-carbon amine is called choline, so that's called phosphatidylcholine, or PC. And then another common one is where the the oxygen, attached to the sulfur is actually the side chain of a serine amino acid. So let's see, what's the right way to do that? I need this to be a stereo. Nope, sorry. Ooh, I drew it wrong in my notes. Shame on me. So this is a serine amino acid with a carboxylic acid and an ammonium group, and that will be PS. And there are some other ones. Different cell membranes have, different cell types have different composition of lipids. Different organisms have different compositions of phospholipids. Notice that if it's phosphatidic acid, the head group is negatively charged. So that's an anionic lipid. Notice that if it's phosphatidyl ethanolamine, the positive charge on the nitrogen cancels out the negative charge on the oxygen. And so this is a Zwitter ionic lipid or neutral lipid, okay? And same thing with phosphatidylcholine is going to be Zwitter ionic, okay? Now, in chapter 23, we talked about antibacterial peptides. We talked about how they were cationic and they would associate with negatively charged membranes. They're going to associate strongly with membranes that have a lot of phosphatidic acid because the head group there is going to be mostly negatively charged. They're not going to associate strongly with membranes that have a lot of phosphatidylcholine or ethanolamine because those are neutral. So that's the selectivity I was talking about between bacterial membranes and eukaryotic membranes. Does that make sense? Got an idea what you guys know what Zwitter ionic means? That just means neutral, though charged. Yeah, go ahead.
That was my question.
Okay. Yep. It's a crazy word. Zwitter, you can pronounce it German or English, doesn't matter. Zwitter ionic means neutral because charges cancel each other out. You guys thought I made that one up. No, that is a real word. Yep. Okay. Let's show you just briefly, because I think you already know this. One more kind of thing that should fall into the class of phospholipids is a class of molecules called sphingomyelins. These are not based on glycerol, but their structure is very similar. And they can be hydrolyzed a little bit. So drawing this structure is a little bit difficult. You need an oxygen, and then a trans double bond here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so a long carbon chain. Then there's a wedge here, a nitrogen here, and that nitrogen is itself tied up in an amide with a long chain carboxylic acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 14 carbons long. So 2, 4, 6, 8, 10, 12, 14. So you can see that that kind of has the same basic structure of a phospholipid, that is 2 nonpolar tails, and then the polar head group is here. There is another oxygen here, which is itself bound to a phosphate group, and then the phosphate group is bound to an ethanolamine that's positively charged. So sphingomyelin is very much like phosphatidylethanolamine in the sense that it also has 2 nonpolar tails and a polar head group. I don't expect you to memorize the structure of a sphingomyelin, but if I showed you a phospholipid versus a sphingomyelin, you ought to be able to tell one from the other. And it's easy. The phospholipid is the one that has glycerol in it. The sphingomyelin is the one that has nitrogen in it. You'll notice the term myelin in sphingomyelin. This type of lipid or phospholipid is present a lot in the membranes of the myelin sheath in neurons. Okay, let's just review something real briefly about fatty acids versus phospholipids. So in the fatty acid, the basic shape is polar head group, which we'll color orange here, and then nonpolar tail, right? In contrast, the phospholipid and the sphingomyelin have a polar head group, but instead of having 1 nonpolar tail, they've got 2. And that makes a difference, which I think maybe I've talked about before, or maybe I haven't. Tough for me to remember. Sphingomyelins, of course, have 2 different kinds of nonpolar tails. So one will be gray and the other will be red. But they have the same basic structure. If you were to allow the fatty acid to wiggle around, what you would see is that it adopts a sort of conical shape like this, whereas the phospholipid adopts a more cylindrical shape like this. The 2 nonpolar tails give it that kind of shape. So you will see that fatty acids associate into something called micelles, whereas phospholipids and sphingomyelins associate into bilayers. The motivation for associating is the hydrophobic effect. This is the same effect we talked about with protein folding, a desire to sequester nonpolar surface area from water. So let's do this with the phospholipids first. This is going to be, don't worry about drawing this down. This is sort of poor man's animation. So when a phospholipid tries to sequester its nonpolar surface area from water, it can do so to some extent by associating side to side. But the problem is that you still would have a huge chunk exposed to water, right? So here is, come on, there we go. Twist, there it is, now it's flat, that looks lovely. So if we were in water, if this in the blue is water, and there's water over here, we got a problem because there's still a bunch of nonpolar surface area exposed to water. So what will happen, at least at the early stages, is a monolayer of phospholipids will actually put its nonpolar groups sticking straight out into the air, because it's better to be in air than it is to be water. And then the polar groups will be in the water. Over time, as concentration increases, what happens is one monolayer interacts with another monolayer, and they put their nonpolar tails together, and then this thing can exist in water with an inside and an outside, And overall, what this is going to make is a bilayer or a vesicle where the polar head groups are here. Then you've got the two sets of non-polar tails here. And then you've got an inner polar head group here. That's sort of a horrible drawing of it, but this allows you to have an inside that's full of water and an outside that is also full of water. And of course, this is the lipid bilayer membrane that's important in cells and in vesicles. This is how we separate some compartments of the cell from others. This is how we separate what's you from what's not you, what's inside the membrane versus what's outside the membrane. Okay, have a happy spring day. I will see you Monday.